Hello, and welcome to the final lecture in this series of lectures on Chapter 9, Momentum, Linear Momentum, for a calculus-based Physics 1 class. And I would like to discuss today collisions especially. I also will talk about the opposite of collisions, and I will perform the calculations corresponding to these slides in separate videos. But let us talk about how the conservation of momentum can be leveraged in a physics standpoint in terms of collisions. All right. Thus far, I want to review the momentum equations that we'll be using in this set of slides. And that was in a previous video. So P vector equals mv vector. And F vector equals dp vector dt. I script I vector, change of momentum, that's the impulse, is the time integral from t initial to t final of sigma f vector dt. Remember, sigma f vector is the net force. Remember, the generalized version of Newton's second law also says that the net force can also be thought of as the change in momentum with respect to time. That is, either mass or velocity, or both could be changing. Well, I want to discuss the idea of conservation of momentum. The whole reason we were defining momentum really in the first place is not just to describe certain motions in a little more detail with things like momentum and impulse, but just like energy, momentum can be a conserved quantity, but it's conserved under different conditions. Let's see what those conditions are. In the absence of net outside forces or external forces of a system that you've defined, so that dp vector dt equals 0 and the momentum is conserved, that is, the total momentum is retained. It may be redistributed amongst objects, but P initial, the total momentum of the system coming in, is equal to P final, the total momentum of the system going out. But again, you have to define what your system is. For momentum conservation, any forces are internal forces. In other words, they're always Newton's third law pairs of forces. In other words, if all the forces in an interaction are always going to be equal in size, opposite in direction, they'll essentially all cancel in the interaction as long as we define the system carefully. So, here's another way to write conservation of momentum. If you sum all the mv initials, then that's going to be the sum of all the mv finals. The net momentum initial equals the net momentum final. So the change in the momentum of the system is 0 kilogram meters per second. By the way, this conservation of momentum thing can be done along one axis, which we will most often do in this class, just say along a horizontal x-axis, or it can be two-dimensional or three-dimensional or so on. But what is super important in order to do this well is to define the system. The system must be isolated. It must be an isolated system for momentum to be conserved. The important concept we must understand is to establish what are the internal momentums, even transfers of momentum, that's going to be conserved versus any external impulses, that would be changes. So in other words, in the absence of any external impulse or external force, the momentum should be conserved. Let's talk about this with a slightly more specific example. Suppose we are playing billiards, or you might just call it pool. Pool and billiards are as close of an example as I could think of to nearly perfect elastic, that is bouncing collisions in physics. So what I'm trying to say is the following, that if a cue ball hits an 8 ball, we can think about a specific example of defining a system. So except for the small amount of friction with air resistance and with the table, the billiards is going to be a good example of conservation of momentum. So suppose the cue ball hits the 8 ball. The question is there a net force on the 8 ball when the cue ball hits? Okay, give you a second to think about that. Okay. But hopefully you know what the answer is. The answer is going to be yes. That's an external impulse. If you define the system of the 8 ball, the 8 ball doesn't have a force on it, and suddenly it then does have a force on it. So that's an external impulse if you're just focusing on the 8 ball only. What about the cue ball? So how about the cue ball? If we define the system instead for the cue ball, that is, the cue ball is our system of interest, then the cue ball is going to feel a force on it that is equal in size but opposite in direction from the 8 ball. Because originally it's moving forward and then all of a sudden it stops. Let's assume the cue ball and the 8 ball are the same mass. So, that being the case, from Newton's third law, these two forces are equal and opposite, but they're different free body diagrams, either the 8 ball system or the cue ball system. So the question is, will we have an external impulse on the cue ball? Well, the answer is also going to be here, yes. Okay? So here, though, is the million-dollar question. What happens if we draw a system circle around both the balls? In other words, if we define the system as cue ball and 8 ball, with that in mind, those two Newton's third law forces, which are both internal forces, will cancel. In some sense, there's no net force on the system collectively. So the momentum of the 8 ball and cue ball system before the collision is the same as the momentum of the cue ball and 8 ball system after the collision. That is to say, if all the forces are internal only, the momentum is exactly conserved. Let me see if I can prove that to you a little bit more mathematically. So, consider an isolated system where two particles interact only with internal forces. So, by Newton's third law, we know that F21 plus F12 vectors equals 0. So suppose somehow these two objects have forces between them. Could be a gravitational force, but some sort of internal force between them. With constant masses, let's assume these are constant masses for now, you can factor out the time derivative. Remember, the time derivative is on dv vector dt, because dv vector dt is acceleration, and if those are the only two forces on each object, then that force creates a net force. And that net force is given by a mass times an acceleration, and that acceleration, the time derivative, can be factored out. So it's m times dv vector dt, but we can factor out that d by dt time derivative. And we can say that has to equal 0 from this equation. Well, suppose we were to sort of integrate this equation with respect to time. On this side, we would just get a constant. So that means the total sum of m1 v1 and m2 v2, those are vectors, for all objects in an isolated system is constant. Because I think if we take a time derivative of any constant and we get 0, that means that quantity is constant with time. So let's say a little bit more about momentum conservation mathematics and what are the real conditions to think about mathematically. Okay? So the idea is that momentum is conserved for what we're going to call isolated systems. So in other words, collisions with no external forces are simpler when they are isolated, when we draw a circle around just those objects that are colliding. That's an example. And then notice that an isolated system has 0 net external force. So if dp dt is the sum of the forces, and that's 0 for two objects, then the time derivative of the vector momenta summed together is 0. Okay? So notice, again, you integrate that with respect to time. You have sort of this notion of initial and final, that an earlier time and a later time, the momentum stays constant. Now, here's one important pitfall I want you to avoid in this class. A lot of times people think, oh, now that I have this conservation of momentum in my back pocket as a tool, I can leverage that in many scenarios. No, you cannot. You must be careful to know if the system is isolated or not. Notice that, let's just take an example of vertical momentum for a falling body. Think back to early in the semester. If you drop a ball, that ball, if you just draw a circle around the ball, is not going to conserve its momentum. because it's going to accelerate. Now here's the deal. That means that the system is only the ball, not the ball and the Earth. So if there's a net force on something that's non-zero, then its momentum is not conserved. Now if you drew a circle around the Earth and the ball, there would be conservation of momentum. It's just that usually we don't look at the motion of the Earth itself, because when you drop a ball, the motion of the Earth is so unbelievably small that we usually ignore it. So just keep in mind, only certain scenarios does it really make sense to define this conservation of momentum. Okay, so I want to talk to you about two types of collisions that you should be aware of, or at least two poles, two extremes, two idealized percentages of the types of collisions that you should be aware of in this class. Okay? The first one is going to be elastic collisions. Okay? And an elastic collision, okay, the idea is that, I already mentioned this out loud, but the objects should bounce apart. Think of the word elastic like, let's see, like rubber or something that bounces. So when objects bounce apart, there's some springiness, and the idea is that after they collide, they separate apart. Okay? Now, with respect to elastic collisions, the momentum of the system is conserved and the kinetic energy of the system is conserved. Now, by the way, no real-world collision is perfectly elastic, but for the sake of this class and for many physics calculations you'll arrive at in your life, you're going to assume perfectly elastic. Now, by the way, in that case, you could try to think of examples that are close to perfectly elastic. Billiards is a good example. Another example would be rubber balls when they collide with each other. The other kind of collision that I want you to be aware of is going to be also what I went over in the intuition videos for one-dimensional collisions, and that is collisions that are inelastic. And the objects don't bounce apart. Instead, they stick together. Okay? They stick together. And since they stick together, the momentum of the system is still conserved, because anytime objects collide, all the forces are internal. All the forces are Newton's third law forces. So they all sort of cancel if you define that whole system. However, the kinetic energy of the system is not conserved when we have inelastic collisions. So you may say, where does some of that energy go? It goes into sound, heat, crumpling, maybe even light, all kinds of things. But the idea is that the kinetic energy is not conserved. You could think of when train cars couple together, or when putty balls smash into each other and they deform. Okay? Those are going to be examples of inelastic collisions. Again, no collision is perfectly inelastic in this world, but we'll assume that for the sake of this class, it's completely one or the other. Now, one thing to note is that bouncing transfers more momentum. That's a reminder from the earlier lecture. There's a greater directional change in the momentum if the object is going to be an elastic bounce. Because momentum is a vector, bouncing transfers more momentum. And no real collision is, like I already said, perfectly elastic or inelastic, but we'll assume that it's one of the two in this class. Okay, so here's just a pictorial way to look at some elastic collisions between these green balls and yellow balls. If they're the same mass and the green hits yellow, green then stops and then yellow starts. If they're moving the opposite direction and then they collide, green takes on yellow's original velocity, and then yellow takes on green's original velocity. And if green and yellow have the same velocity, but green catches up to yellow, they hit together. Green then starts moving slower and propels yellow forward. So again, they trade velocities whenever the masses are equal. Okay? So, again, momentum and kinetic energy are conserved for a purely elastic collision. Now, in one dimension, for an elastic collision, these are the two equations you should be aware of. Conservation of momentum, conservation of kinetic energy. So P1 initial plus P2 initial equals P1 final plus P2 final. That's for two objects in one dimension. And then K initial plus K2 initial equals K1 final plus K2 final. Okay? Now, I will perform this long example in a later video, but suffice it to say we have to use two equations, two unknowns, but the second equation is a quadratic equation because it's the kinetic energy equation. So that's kind of hard to solve. So I will show the steps, and then I will show how to simplify that on the next slide here. Now, suppose you solve those two equations, two unknowns. I do not want you to repeat that last calculation over and over again. So there's a general textbook equation formula for this. And it turns out that some poor grad student, maybe, solved for the final velocity of each object in one dimension in terms of m1, m2, v1 initial, v2 initial, in general for elastic collisions. And we thank them. Because in order to get these equations I'm about to show you, it was a lot of effort, but they are general recipes that do work. So notice that if two objects undergo a one-dimensional elastic collision, then the final velocity of object 1 is given by this equation, and the final velocity of object 2 is given by this equation. So let's take a look at these two equations. Notice that the final velocity of mass 1 depends upon the difference between the masses, mass 1 and mass 2, over the sum of the masses. Notice that if mass 1 is larger, this will end up being more so a positive influence, and then if mass 2 is larger, this will be more so a negative influence on mass 1's final velocity. Notice that mass 2 matters more, though, because of the transfer to mass 1's final velocity, because there's a 2m2 in this term coming from object 2's initial velocity. Again, you divide by the sum of the masses. And then look, these equations are somewhat symmetric, except it's 2m1 over m1 plus m2 times v1 initial for the first term of v2 final, and then v2 initial times m2 minus m1 over m1 plus m2. Okay, so I will perform this example, which is next, in a later video, okay, which won't take extremely long. What about inelastic collisions? Inelastic collisions, when objects hit and stick, okay, if they are equal mass, but they're moving in opposite direction, they should hit and stick and stop. Notice the energy definitely gets transferred into crumpling, sound, heat, all kinds of things. How about if two objects are moving in the same direction, but one rear ends the other? Notice they're both going to move in the direction that they were moving, but slower, because now you have a combined mass of the system, if you will. Okay? So when it comes to inelastic collisions, only momentum is conserved, not kinetic energy. And for one dimension, you only have one conservation equation. But the idea is that the kinetic energy not being conserved allows us to come up with a much more simple equation, because this is a combined mass. By the way, feel free to check out these web links in terms of simulating elastic versus inelastic collisions. So with inelastic collisions, there's one system after the collisions. So the general equation is going to be much easier than elastic, and it's going to look like this for two objects. M1 V1 initial plus M2 V2 initial equals M1 plus M2 times V final of the system. Why V final of the system? Because both objects move with the same velocity after combining. So notice that there will only usually be one unknown, because the masses are usually known and the initial velocities are usually known. So you can just solve by division there. So you can perform this inelastic collisions example, and I will do that in a later video. Now, what is an explosion? Let's shift gears here just a little bit. An explosion is the opposite of a collision. The particles first have a brief, intense interaction, then they move apart from each other. Imagine like fireworks, or say an object just explodes horizontally in one direction. Okay? So, you can imagine that an explosion might be something like if a plate hits the floor and it flies into several pieces horizontally. The initial momentum in many cases of an explosion is 0, and then after it explodes apart, all the vector momenta are in multiple directions, but they add to 0. Okay? So the explosive forces are internal forces, and as long as the system is isolated, the total momentum during the explosion will be conserved. Okay? So I will do an inelastic separation, almost an inelastic collision in reverse here, and perform this example again in a later video. So stay tuned for that. How about when collisions are two-dimensional? When they're two-dimensional, the momentum is a vector. So it has both an x and a y component. Those are both conserved. Okay? Now, by the way, those are both conserved in both elastic and inelastic collisions. If additionally the collision is elastic, then the kinetic energy is also conserved. The nice thing about elastic collisions in two dimensions is many times the problem can be overposed. In other words, as long as you know the initial masses and velocities, you can either solve any one of these three equations will work for solving. Okay? So a good example of this would be, say, playing billiards. Notice that this is like a time lapse of strobes of a cue ball hitting, say, an 11 ball here. Notice when the cue ball hits the 11 ball and bounces off two-dimensionally, the 11 ball starts to move. But notice that the momentum in, which is, let's say, in the positive x direction, is equal to the momentum out, which is in the positive x direction, both the cue ball and the 11 ball. But the y momentum, which was initially 0, is the same thing as the positive y momentum that 11 has and the negative y momentum that the cue ball has. Okay, so this is exactly what this two-dimensional problem is going to be, and I've typed this entire one out, and I will show this also in a later video. And it turns out billiard balls are very special. If they have the same velocity and they undergo an off-center collision, so it's not one-dimensional, it turns out that something very special is going to happen with the sum of these angles. Okay? All right. The last new concept, you notice the slide really slides over, that I want to introduce is center of mass. Okay? Center of mass could be discussed later in the semester, but I want to discuss it now because I want to define momentum in a slightly different way if we can use center of mass. Think of center of mass of the centroid as the centroid, or the balancing point of an object's mass. Okay? It's the mass point where all the mass can be thought to be collapsed onto. Okay? So remember, like the centroid of a triangle is you take, like, say, each median and you intersect it in the center. Okay? And you get the balancing point. Okay? So the idea is that you could imagine if all the mass were concentrated at that point, that's one type of center. That's different than, say, the orthocenter or there's other kinds of centers for objects. Let's see. An unconstrained object, in other words, not on an axle, with no net force, rotates around its center of mass. Notice that this person that flips, notice we haven't talked about rotation much yet this semester, but they're going to rotate around their center of mass. So an unconstrained object will rotate around its center of mass. That's why it's important. In fact, earlier in the semester, you may recall that many times we've looked at free body diagrams. So here's a real simple free body diagram of an object. And free body diagrams from Newton's second law, when we drew a dot near the center of the object, that dot was the center of mass. By the way, center of mass and center of gravity are roughly the same thing. The only difference between center of mass and center of gravity is, as long as the gravitational field everywhere nearby is uniform, then center of mass and center of gravity are the same. But this center in the geometric center here, if this is an equally weighted box, thinking back to dynamics and Newton's laws, that dot in the center was the center of mass. So when we were looking at forces on an object, those forces could be thought of as acting on the center of mass. How about if you throw a golf club? A golf club will rotate near the end, near the head, where it's like heavier. Okay, so that's an example of identifying the center of mass. How about if you roll a bowling ball? A bowling ball center of mass should be in its geometrical center. Another important application of center of mass is toppling. Toppling over an object like a long-haul truck versus a sports car. A long-haul truck has its center of mass much higher. A sports car has its center of mass much lower. And as a result, a long-haul truck in, let's say, the wind can much more easily blow over because it doesn't have to rotate as much of an angle to topple versus a sports car has to rotate through a much larger angle to have it topple. So when the center of mass is sort of closer to the ground, for stability, it makes a difference. Okay? How can you experimentally determine the center of mass? Notice that the center of mass can be determined by taking an object and hanging it and drawing lines, and if you hang it from multiple positions where those lines intersect, again, that's the centroid, or center of mass. Again, center of gravity is the same thing as center of mass, as long as the gravity field is uniform. Now, interestingly enough, center of mass doesn't even need to be where mass of the actual object itself exists. Let's think about an easy example. Suppose we have a meter stick. You know, if I hold in the geometrical center of the meter stick should be balanced. So its center of mass is in the geometric center. But notice, suppose a person with a heavily weighted board sits on a seesaw. Notice that the person here and the heavily weighted board are balanced because the fulcrum, which is like the top of this triangle, is balancing over the center of mass. Look at the Leaning Tower of Pisa. Notice the Leaning Tower of Pisa is leaning over, but its center of gravity, and thus center of mass, you could imagine, has not yet moved past the edge of the object. If that vector were to be out here past the edge of the object, so if it were tilted further over, it would actually start to topple. And let's look at one more example. Look at this boomerang. We know a boomerang should rotate around its center of mass when it's unconstrained, not mounted on an axle. But notice the center of mass can exist where there's no object itself. So it's on the concave side of the boomerang, and the center of mass, interestingly enough, can exist right there. So why don't we talk about the center of mass mathematics? In momentum problems, it's often useful to analyze the motion of a system of particles or an extended object. Suppose you have a three-dimensional system of masses. The total mass, let's say, is capital M, and the center of mass of all those objects is M1 R1 vector plus M2 R2 vector plus M3 R3 vector, and so on. By the way, R here is the position vector that we defined back in chapter 4. It's the position vector that has its tail at the origin and its head out there somewhere in space. And if you add up all those mass-weighted position vectors and divide by the total mass, you get the center of mass. Notice this is the mass-weighted position of all masses. So you could write this equation in a more compact way, 1 over big M, sigma over I is just a counter of mi ri vector. Now, by the way, that's a system of point masses. If it's a continuous distribution, suppose you're looking at the center of mass of a baseball bat or something, there's continually mass sort of everywhere in the same object. So in order to get the center of mass, you'd have to think about what's the position of each little element of mass, integrate them all up continuously, and divide by the total mass. Now, by the way, in general, that's kind of difficult to do. dm has to be usually expressed as some sort of position function. Usually we express that in terms of, like, say, density and volume or some sort of position function. Now, what if two masses exist in one dimension? The center of mass is going to be m1 x1 plus m2 x2 over m1 plus m2. Notice that this is basically just the weighted average weighted average position of these masses. Notice that the masses are basically the weights, and x1 and x2 are the positions to get the x center of mass. Notice that, suppose you have mass 2 larger than mass 1, then the center of mass, which is often denoted with a circle and a kind of a plus through it, that is going to be the position of the center of mass, and it's going to be closer to mass 2 than mass 1. Okay? So by the way, think of weighted averages like when you calculate your grade. Certain assignments are worth more points than others, so when you calculate your grade, think of M1 and M2 as the number of points, and X1 and X2 as your grades, and XCM, the center of mass, is kind of like your weighted grade, your current grade. I hope that makes sense, especially to those of you that are students. Again, center of mass is closer to the larger mass. So here's an example of the Earth and the Moon. Again, I would work this out on a later video. But skipping ahead for now, let's look at the motion of a system of particles. In many situations, a system can be treated as if all the mass were at the center of mass. So total momentum is total mass times the velocity of the center of mass of the system. And it turns out even the net external force, so the net force, is the time derivative of the total momentum vector, which again depends upon center of mass. So analyzing linear motion of an extended object is identical to analyzing a particle at the center of mass. So analyzing linear motion of an extended object is identical to analyzing the particle. And remember, we've defined the particle earlier this semester. We often just track a single particle, and that is just the center of mass of that multiple extended object, or many objects all moving around. Okay? So the basic idea is, look, here's an example. Notice that this is linear motion plus rotational motion. If you throw a wrench forward, notice that it rotates around its center of mass, but then also it has linear motion forward, even though it's an extended object, around its center of mass. Okay? This example basically says that if the projectile pieces go out in multiple directions, notice that the projectile in center of mass in the absence of air resistance should follow this parabolic trajectory. But the pieces could launch out like this and like this. But notice that those will cancel in terms of the leftward and the rightward momentum. And maybe one piece launches over here and one piece launches way out over here. But the idea is that even though the many pieces launch out many directions, the center of mass of all the pieces will still follow the same trajectory as if it had never exploded. This is why it's so useful to analyze with center of mass. So this concludes this lecture. Please smash that like button and give it a thumbs up if you enjoyed this video. Please subscribe to the channel and share it around with people you know to help grow the channel. Thank you so much for those of you that support the channel, and to my students, and I will plan on seeing you in the next video.